Nick Payton here from SigOpt. Thanks for joining us today for a conversation around hyperparameter optimization as part of the broader approach to building a modern modeling stack to support all your model development efforts. I'm responsible for marketing here, and I'm joined today by Scott Clark, our co-founder and CEO. During this talk today, Scott will be drawing on a few lessons from some of our bigger enterprise customers with whom we work to scale their model development process with a combination of experimentation and optimization tools. Following on a presentation he gave recently at a conference in San Francisco, TWIMLcon, Scott will be building on a framework around how to think about your modeling stack, some of the critical capabilities that you need to build into that stack to be able to efficiently scale your model development efforts and build the best models, and really focus today on double-clicking on one aspect of that part of the modeling stack, specifically some of the more advanced optimization techniques that your team can build into your stack to really boost and supercharge some of your modeling efforts. So whereas at the conference, Scott was talking at a high level, and we'll be sharing that video with everyone soon, now he's going to go a little bit deeper on some of the more advanced components, specifically the algorithmic components that you can access through an API using our product. The context here, though, is to focus much more on use cases and applications for these solutions, as well as give you some background on some of the research underpinnings that support the algorithms that we've developed and integrated into our solution today. So without further ado, I will hand it off to Scott, and he'll take it from here. Thanks, Scott.
Excellent. Thanks so much, Nick. And thank you all for joining me this morning. Really looking forward to diving deeper on this. Throughout the entire presentation, if you have any questions, please make sure that you just put them into the GoToWebinar question dashboard, and Nick will moderate those throughout the talk, and then we'll leave some time at the end as well. As Nick said, we'll be talking about advanced optimization for the enterprise and walk through the intuition behind some of the features that we've developed at SigOpt, as well as some real-world use cases and motivation for how they can be potentially applied within your business. And SigOpt was really founded to help attack these types of problems. Our mission as a company is to help accelerate and amplify the impacts that modelers have. And the way that we accomplish this is through our experimentation and optimization tools. And we have a set of advanced features that really help extend the capabilities of this beyond what traditional experimentation or hyperparameter optimization or neural architecture search that might be being done in the modeling workflow today. And really unlocks the ability to really get the most possible impact out of these massive investments that you've been making. As Nick mentioned, there's obviously a large set of things that need to be considered when building a modeling framework, thinking about the larger stack of tools that you want to provide to your users. In that TWIMLcon talk, I go into a lot more detail about different trade-offs of each of these, different ways that you can decide what's worth investing in, what's worth partnering, and etc. And I highly recommend checking out that talk. I'll be double clicking, as Nick said, in the experimentation and model optimization component of this workflow. This is a critical component to doing modeling. All modelers require the ability to do experimentation. You're trying new data sets, you're trying new features, different architectures. Every single model, from the simplest random forest where you need to select the number of trees to the most complex neural network where you're setting architectures and hyperparameters, requires experimentation and tuning to get it to its peak performance. So I'll be focusing on how to solve this problem, how to use advanced tools to unlock the ability to get the most out of these models that you're building today. And oftentimes this can be an overlooked component of the modeling process, but when attacked well, it can actually lead to significant improvements and massive additive benefit in addition to all the other investments that you're making in things like the frameworks themselves, the hardware, the data preparation, and the productionalization. So I'm really going to go through four modular components here, and these represent kind of different approaches, different features, different ways that you can solve some of the problems that your modelers are faced with day in and day out. At the first one, I'll talk about solving black box optimization problems and how you can phrase some of the experimentation problems that you have today as a black box problem that can be readily attacked by things like Bayesian optimization or the larger Bayesian and global optimization ensemble that SigOpt provides. I'll be talking about how to rephrase some of these problems in the second section to handle multiple competing metrics. In the third section, I'll talk about how leveraging the full breadth of the infrastructure investments you've already made is really important when making sure that you're efficiently solving these problems in the real world. And finally, I'll end on how to apply these techniques even to the most time-consuming and expensive models that you may have. You can think of it as the big deep learning or reinforcement learning strategies that might take hours or even days to train. How do you even begin to attack those with better optimization? So each one of these sections will have the same format. I'll motivate the problem. I'll talk about some of the research and intuition behind it, and I'll end with some examples. It's worth noting that I'm only going to be touching at the surface of the different capabilities offered by the SigOpt platform. I'll be focusing on these four specific components, but there are many other components that we've designed to help attack the real world problems we've seen by building our applied optimization engine over the better half of the last decade. So if you have a problem that doesn't cleanly fit into one of these four buckets that I'll be going over today, we would love to talk with you afterwards and talk about maybe some of the other features that we've developed that can maybe more readily attack a different problem. So again, we're just scratching the surface here and we're highlighting these four specific examples. So first up, I'll talk about black box optimization. This is really about how do you take this experimentation process that your modelers are performing today and make it more efficient? How do you take all of the different tunable configuration parameters that are inherent in a modeling process, again, from feature embedding parameters that are very common when you're doing NLP or video or speech models? How do you take the architecture parameters that are really inherent in a lot of the deep learning models that people are leveraging today? And how do you take all the different hyperparameters inherent in every type of machine learning model and make sure that you're getting to the best possible version of your model as efficiently as possible? And this can have wide-ranging effects on the process itself, from amplified performance, getting to better results, productivity gains of your experts. Again, you might have specific domain expertise or context awareness that allows you to attack a problem very uniquely, but tuning that system is inherently a separate trial and error-based task. So freeing up that expert time in order to solve that can be incredibly important. And this in turn leads to accelerated modeling, both in terms of wall clock time and compute time, which hopefully means you're producing more models, not just better models or saving time doing it. So SigOpt attacks this problem by providing a simple API REST interface to an ensemble of Bayesian and global optimization methods that help us to solve these black box optimization problems that are inherent in the modeling process. And the way that that actually works is by bolting on top of these models that you're building today. So again, you've applied a lot of domain expertise and context awareness about the application that you're trying to solve in order to collect and clean whatever data you might have, select what approach you're going to take, whether that's traditional machine learning, deep learning, reinforcement learning, or maybe an entirely proprietary algorithm. You have different ways to evaluate the efficacy of these models. It could be something like accuracy for a simple classification model. It might be a back-tested Sharpe ratio for an algorithmic trading strategy. It might be the amount of money you lose to fraud in a credit card fraud detection strategy. But again, A lot of that requires domain expertise and requires a lot of context awareness for what to build, how to build it, etc. But again, throughout this entire system, there's lots of these tunable configuration parameters that affect how well this system performs overall. Feature parameters, architecture parameters, hyperparameters, etc. So the way that SigOpt works is by bolting on top of these investments that you've already made and basically helping you with that configuration, tuning, and experimentation. First, you define what you can tune about the system. So maybe the number of trees in a random forest or the learning rate of a convolutional neural network. SigOpt then suggests specific configurations for you to try. So specific sets of hyperparameters or architecture parameters, etc., which you then evaluate on your system and report back how well they've performed. What this means is SigOpt is never directly accessing the model or the data itself. So we can think about this as a black box problem where we're uncertain as to what's happening underneath the hood here. All we can do is observe the output given a set of configurations that we've given to you, which makes this an entirely black box problem. And SigOpt's ensemble of Bayesian and global optimization techniques allows us to, in this global derivative-free way, extremely efficiently search that configuration space, driving you to the best version of this model, whatever it may be, as efficiently as possible. And we do this leveraging a lot of different techniques from the academic literature, things that we've developed ourselves, having written a lot of the open source in this field and continue to actively contribute to it with our dozens of papers at ICML, NeurIPS, etc. But the way that we attack this problem is fundamentally trading off two things. We want to explore the underlying parameter space to learn as much about it, and then exploit that information to guide you to the best possible configurations. And in the academic literature, this is often called things like sequential model-based optimization, adaptive design of experiments, intelligent global optimization or search. And the way that it works is relatively straightforward at a high level. First, we take the information of what we've sampled so far, and we build a statistical model for it. That's this upper left component here. Many times, people use classic statistical models here, like Gaussian processes or Parson estimators. This is a representation of what we've sampled so far, like these 5 points here, and what we think could happen if we were to sample other points in that space. So our goal is to say, given what we've observed so far, what do we think will happen in the unsampled areas? And so we can build a statistical model there and leverage that to decide what's the most intelligent thing for me to try next in order to hopefully optimize, or in this case, maximize this function or this black box that I'm tuning. So we apply what's called an acquisition function to this statistical model, and we're able to say, what's the point that has the best expected improvement or the best probability of improvement over something that I've seen previously? This guides us to a specific point to sample, which we then, again, return to be evaluated. That is then evaluated and updates our statistical model and basically gives us a new representation of the world. Now we have, instead of 5 points where we've sampled specific hyperparameter configurations, for example, now we have 6 points. And you can see we've fundamentally changed what we think will happen in that region of the hyperparameter space. And now all of a sudden there is very little utility in sampling there again. So we've explored that region of the space. And then now we're going to exploit some local knowledge that we have here in order to try to get to a higher value. And this sequential model-based optimization basically takes this premise and wraps it in a loop. So as we sample more points, we get a better statistical view of the world. As we get a better statistical view, that guides us into deciding what to sample next better. Eventually, we'll start to sample these other regions of the space, and it ends up being an extremely effective global optimization strategy. How this differs from things like simulated annealing or population-based algorithms or other kind of classic global optimization strategies is because we're doing a lot of the work on the statistical model and building up these different surrogate representations for the underlying time-consuming and expensive process we want to optimize, we end up sampling that underlying process much less frequently. Basically, all of the heavy lifting is done in the Gaussian process world instead of on the function itself, which equates to orders of magnitude savings in terms of how many times you actually need to train or sample that underlying machine learning or deep learning system. And this can be incredibly important when it can take minutes, hours, or even days to evaluate that system. You want to do it as infrequently as possible. And that's where Bayesian optimization really shines. Unfortunately, Bayesian optimization has a lot of tunable components in itself. After writing Mo, or the metric optimization engine, based off of my PhD thesis many years ago, a lot of people that I went around to go promote the software to said that they had an optimization problem, and with the software that I developed, now they didn't have an optimization problem anymore, they had an optimizer problem. And that's because a lot of the research-focused open source out there is very good at pushing the field forward and publishing papers, but it leaves a lot to the user in terms of tuning things like which surrogate functions to use. Is it Parson estimators? Is it Gaussian processes? Which covariance kernels do you pick? Which acquisition functions do you pick? All of these decisions about the optimizer itself can have a massive effect on that statistical view of the world, whether it's very clean or very noisy. It can have a massive effect on which points are actually suggested to try next, whether you're doing things like trying to find the point with the highest probability of improvement or the highest expected improvement, or trying to use other information theoretic measures. Basically, at the end of the day, there's a lot of these trade-offs that need to be made in order to have an efficient global optimization strategy. And this is often the pitfall that people run into when applying things like open source Bayesian optimization, and even comparing it to other naive methods like randomized search. An untuned Bayesian optimization method can sometimes lead you astray because, similar to an untuned machine learning model, it was tuned to a specific purpose that might not be similar to what you're attacking. So one of the reasons why we built SigOpt after releasing a lot of this open source was to help solve this problem by ensembling all of these different methods together. Ensembling many different surrogate methods, automatically tuning and trading off different covariance kernels, acquisition functions, etc., and really taking that optimization problem and solving it instead of just shifting it into needing to become an expert in optimizers themselves. And we've written a lot, both in the academic literature, again, at a lot of ICML and NeurIPS and AI Stats papers and workshops, but we also have quite a bit in our blog itself too, that go into some of the intuition behind the covariance kernels, Gaussian processes, different ways to optimize them, etc. All of these are the different trade-offs that you need to make in order to build a good Bayesian optimization system. And all of this happens underneath the hood automatically as part of SigOpt's service. So that gives you a high-level overview of the kind of general purpose Bayesian optimization or black box optimization problem that we're trying to solve. And that can be extremely powerful if you have a well-behaved function that you understand the parameter space, you can sample it relatively quickly, and you understand what you're shooting for. But one thing that we found is that can be a great replacement for some of the open source or some of the brute force approaches that people use today, or even the manual search approaches people use today. But in the real world, there's often many different kind of variations on this problem that can make it a little bit more intractable versus kind of the standard classically defined black box optimization problem. And so the remaining 3 sections, I'll go into ways that we attack this more directly in this more applied real world case, leveraging the 5+ years of experience on the research and platform side of SigOpt by deploying this to our customers around the world. The first of which is how to use optimization methods to optimize competing metrics. So the reason why this is important is very often in the real world, and especially in the research and development stage of a machine learning model development, you often don't know exactly what you're shooting for, or you might not know what's possible in terms of the performance of the model that you're building. What this could mean is you might have multiple competing metrics, like you need something to be accurate but also robust. You might be building a trading strategy that needs to make a lot of money, but also trade a lot of money or have limited risk. You might have different thresholds into maybe you're deploying a deep learning system, but it needs to fit on an edge device. So it needs to be as accurate as possible, but minimize things like inference time, memory footprint, power consumption, whatever it may be. The real world is fraught with all of these kind of competing things that you need to trade off. And you may not know ahead of time what's even feasible with your model or what's necessarily the best possible thing to attack that unique application that you're driving towards. So by rephrasing this problem as a multi-metric problem, we can basically optimize multiple of these underlying objective metrics simultaneously to give you as an expert a set of potential good configurations to then choose from. So we take our classic problem of black box optimization that I showed before, and instead of taking a single objective metric down here in the bottom, now we want to take in multiple things that you may care about. Again, speed versus training time, training time versus accuracy, maybe a Sharp ratio versus a book size, maybe it's accuracy versus power consumption, whatever it may be. There can be multiple optimized metrics, and there can be multiple metrics that you just want to keep track of throughout the optimization process. So again, instead of getting you one single best answer, the goal here is to get you a set of answers, a Pareto frontier of efficient trade-offs between these underlying objectives. So you may have one objective that's optimized in this region of the space, one objective that's optimized in this region of the space, and you want to know how exactly you can trade these two things off in order to make the decision post hoc of which one you want to put into production or explore further. And again, in the real world, we see this time and time again where things don't often cleanly fit into a single metric that's difficult to normalize, et cetera, but you need to be able to do this in neural networks, materials design, control systems, et cetera. And this is a great problem with, it's an active field, an active area of research in the academic community. There's different ways that you can try to attack this by basically breaking up your function into subcomponents, or maybe you want to explicitly optimize one metric first and then slowly start shifting over and optimize the other metric. So instead of having this single problem, you break it up into many sub-problems that you're trying to independently optimize and then have a Pareto frontier at the end. This is akin to just trying different maybe normalization parameters of a composite metric as opposed to explicitly solving the multi-metric problem directly. But it can be a very powerful way to rephrase the problem. There has been a lot of great research, though, fairly recently, up into this paper in 2019, which allows you to explicitly reformulate the problem to attack it more directly. So instead of trying to optimize maybe the expected improvement of a single metric, what we're going to do is we're going to try to optimize it across both metrics, both taking into account which regions we're interested in and any potential constraints on the metrics or the parameters themselves. What this allows us to do is, instead of explicitly trading off between two independent functions that we're trying to optimize, especially for slightly more complicated spaces, this allows us to explicitly decide which regions of the Pareto frontier we want to zoom in on, which regions we want to continue to explore, or exploit, and do that jointly across both metrics simultaneously, getting the most efficient way to get to the underlying Pareto frontier, sampling that underlying function as infrequently as possible. And again, this is a very active field of research. One of the main benefits of having a full-time research staff at SigOpt is being able to not only contribute to that research, but constantly be pulling in things like this from the academic literature, adding it to our ensemble, and making sure our customers, again, don't have to have this optimizer problem that's inherent even in the most simple phrasing of the black box optimization problem, but really know that they're always getting the state of the art when it comes to even these more sophisticated problems like multi-metric optimization. This can be further extended by putting explicit constraints on the space, on the metric space itself, saying things like, I only care about accuracy versus inference time when inference time is above a certain level, or in this case, I care about performance throughout the entire spectrum of potential outputs, but there's a minimum level of stability that I'm willing to consider. And so we can explicitly, again, with this better formulation of the multi-metric problem, say, not only do I want to intelligently sample that Pareto frontier, but I want to force it to sample specific regions in the metric space. Further extensions of this are constantly being developed as well, and basically any way that you can formulate that underlying multiple competing metric problem, there's a way to tune the optimizer in order to better address that problem. So we have some examples that we've done with some of our partners. Here I'm showcasing one we did with NVIDIA that go into quite a bit more detail in this. They include specific examples with open data sets. The code is available on GitHub, and you can kind of reproduce some of these problems yourselves. And they can result in significantly higher accuracy with lower training time, or be able to make specific trade-offs in terms of accuracy versus inference time, things that would be lost if you were only kind of tuning towards one metric blindly or myopically without taking into account some of the real-world constraints or other competing metrics that you may care about. I won't go into too much detail here, but in the post it talks about taking a kind of a classic question and answer natural language processing problem, tuning various hyperparameters, architecture parameters, etc., and then showing that you can get significantly better results than not only the tuned baseline from, in this case, the Facebook AI research paper, but also significantly better results than exhaustive or semi-exhaustive random tuning. At the end of the day, what this means, though, is faster wall clock time, better performance, and better resource utilization in the sense of less money being spent per percent gain in that underlying method that you're trying to optimize for. So the next section I'll talk about, which is more about leveraging the infrastructure resources that you've already developed. So obviously, all of your modelers have this black box optimization problem of needing to tune their underlying models. Again, this is very orthogonal to the domain expertise required to actually understand the problem, understand the data, etc. But it can have this additive benefit in getting the best version of those models. Then I talked a little bit about how you can rephrase that problem to solve multiple competing objectives, how you can solve these more real-world black box problems that don't necessarily fit within the clean constraints of the typical way this is phrased in the academic literature. And now I'm going to talk about how you can take the system that you've already built today that might allow for things like parallelization or larger compute, and use the same system in order to get to the best results as efficiently as possible. So by optimizing multiple configurations in parallel, we can have faster time to results. We can leverage the cluster that you may have already invested in and scale with whatever infrastructure, both on-prem or in the cloud, that you may have. This is more about research productivity in terms of wall clock time to get to these results, which can allow for faster iteration. Basically, again, what we do is we take that same interface that we've been talking about before. Again, we can think of that underlying model as a black box. It's just a computational resource that we can query with specific configurations and receive a response back. And what we can do with our parallel use case is basically act as a resource scheduler for many of these independent parallel workers. So each of them are just resources that can be queried with specific configurations, specific architectures, specific hyperparameters, etc. And each returns a response, potentially asynchronously. And what SigOpt does is it conditions on the history of everything it's observed from all of the independent workers that are only talking with SigOpt, not necessarily each other. But it can also keep track of all of the different resources that are currently working on different tuning tasks, and then say, given the true history of everything I've observed, the outstanding history of things that I know are running, what's the most intelligent thing that I can then give to a new free resource in order to optimize this black box optimization problem. And again, this takes a rephrasing of the underlying black box optimization problem as it's traditionally written in a lot of the open source or in the academic literature, and basically says, instead of sampling a single point or wanting a single point to try next, how do we rephrase that problem to try to find multiple points to suggest to do next? And what this may do is take a problem like this, where we have 3 data points, we have a relatively noisy statistical model here, and we may want to sample the far left side if we can only sample 1 point. But if we can sample multiple points in parallel, then that allows us to do things like explore a bit more and sample this point in the middle in addition to the point on the edge. At parallel bandwidth 3, it's still exploring. But at parallel bandwidth 4 and 5, what it's doing is it's taking advantage of the fact that it can actually sample multiple things simultaneously to further resolve or exploit potential local optima within this region here. So what you can see is, well, naively, if you could only sample things sequentially, you might have done this first, and then this second, and then this third. If you can leverage for effectively marginally 0 wall clock time, a parallel set of workers, then you can get quite a bit more information and go further down that exploration and exploitation trade-off by just leveraging the fact that you can sample more things simultaneously. So we have some examples of this. This is some joint work that we did with AWS, where we basically show the inherent speed up between moving a job from a pure CPU workload running sequentially to a GPU workload running in parallel. You get a benefit from switching architectures, computational architectures, the underlying chipset, as well as a benefit by using more sophisticated optimization methods. And it turns out that this is a multiplicative benefit. So doing one is great, but doing both can be several orders, a very high order of magnitude speed up here in terms of being able to get to the best possible response. So this is a relatively straightforward problem that we go into much more detail in the blog post on. But basically, we take a simple natural language processing problem of classifying sentiment of movie reviews. We tune various hyperparameters and architecture parameters, both kind of the classic ones around learning rate or gradient descent hyperparameters, classic architecture parameters for a convolutional neural network. But we also tune in the embedding dimension of a word to vec kind of pre-processing step as well. This just kind of goes to show the full breadth of different kind of magic numbers or configuration parameters that usually exist within a complex machine learning or deep learning workflow, and just goes to show all of the different things that you can potentially tune when having access to an optimizer. what we show in this post is by leveraging the more intelligent Bayesian optimization methods backed by SigOpt, we're able to get to better results in less number of observations, even while leveraging the fully parallel compute available within AWS. So again, you can get to the better results sequentially, but also still maintain the ability to do that when optimizing in parallel as well. What this means at the end of the day is you can take a job that would be extremely expensive or extremely time consuming and be able to knock that down into a much more tractable set of time. So several days to 1 day, lots of money to less money, and ultimately getting to a higher percentage gain in terms of the metrics that you're optimizing for less computational money. And again, it's just worth noting that there's often many of these tunable configuration parameters that live throughout a machine learning pipeline. So you have things that are traditional hyperparameters that people will readily tune either via brute force or manual search, things like learning rate, etc. But more often than not, when you think about your model more holistically, there's tunable parameters in the feature space, there's tunable parameters in the architecture space, as well as that traditional hyperparameter space. And there might be even more tunable parameters in the hyperparameter space than you may tune today if you're constrained by more limited brute force methods. And so really what we like to encourage our users to do, and we've seen great gains with a lot of our customers, is by opening that up and solving this problem more generally by tuning the larger configuration space that's inherent throughout the entire process. And you can get significantly better results by doing that. So I'm going to wrap up this fourth section by talking about how do we attack problems that are extremely time-consuming and expensive to actually evaluate. So obviously everybody has this black box optimization problem. You might have multiple metrics you want to optimize. You might have a lot of independent workers or independent machines that can evaluate these methods. But what happens when even evaluating a single model is so time-consuming and expensive that you might not want to go through that optimization feedback loop even dozens or hundreds of times? And that's really where a lot of the literature has been shifting to in terms of things like early termination, monitoring the training of a method and stopping it early potentially, or more advanced methods like multitask optimization. So what this allows you to do is take a very time-consuming and expensive method model and break it up into smaller components, which then can give us cheaper, noisier information in order to optimize the full model more efficiently and do it with fewer total configuration samples. So what we're doing is, again, taking that classic problem of just tuning a black box underlying technique, and we're focusing on how do we go through this optimization loop in as few times as possible? How do we take a method that might take a day to train and be able to get to decent results in a week instead of over the course of months or the years that would be required with a grid search or random search? So there's been some great research recently in this field around multitask optimization. And the fundamental intuition here is, how do we, again, take a model, a full cost model, and break it up into smaller chunks? In this case, a chunk that takes 1/4 the time to evaluate, 1/16 the time to evaluate, or 1/28 the time to evaluate, and learn cheap, kind of lower fidelity information about the underlying system in order to exploit that when tuning the full cost, more expensive model. You could think of this as maybe taking less data and getting a noisier version of your model faster. You could think of this as maybe going over fewer epochs, so you get a faster result, but it may be a little bit more noisy or uncertain, or some combination of the two. This could even be extended to maybe algorithmic trading back tests where you have a coarser replay of the market, or even physics simulations where you might have a looser mesh or something like that. Basically, you can sample a cheap, noisy version of the model to learn which region of the space is worth sampling, and then leverage that to sample increasingly more expensive versions of that model, ultimately resolving the global optima in the space that you actually care about, but sampling it much less frequently so you avoid regions, like in this example, which might not be worth sampling at all. So the trick behind this is to basically take these underlying methods that are correlated, potentially correlated, and represent this kind of cheaper, noisier piece of information, and then use that to decide what's worth sampling. And given how expensive that underlying task is, when is it worth sampling the cheaper one in order to get information about the more expensive one? There's quite a bit of active research in this field, but one takeaway is this type of method, backed by intelligent adaptive design of experiments, like the Bayesian optimization ensemble within SigOpt, can get to much better performance, orders of magnitude more efficiently than classic methods like random search or naive adaptations of random search like hyperband, which basically just do random search but kill things early. By explicitly optimizing across the parameter space and this task space, we can get to significantly better results than traditional Bayesian optimization methods, and quite a bit better results than naive brute force methods. So we go into quite a bit more detail in this example that we did with MLConf, where we take the Stanford CAR data set and we show that in this expensive computer vision task of multi-class classification, how do you break that into subcomponents in order to get to the best possible model? So we take and again, we go into more detail in the blog post, and all of this is available online, but we take a kind of classic architecture for doing computer vision classification problems, the ResNet architecture. And we show that by tuning more expensive versions of it, like fully fine-tuning all of the convolutional layers, even after it was pre-trained on something like ImageNet, versus just tuning the fully connected layer, we can get significant performance improvements over the baselines available, and just pulling this off the shelf via an open source repository. One interesting thing that we found here is by just tuning these 7 different hyperparameters, we were able to efficiently leverage this multitask optimization method to get to significantly boosted performance in both a larger network as well as a much smaller network. There's 2 interesting insights here. One is that not only are there significant potential gains to be had by tuning a method that's already been pre-trained on something like ImageNet, that's already very well understood like ResNet. But one interesting thing too is by going back and retuning those parameters and then allowing the network to fine-tune itself by allowing it to learn over the larger space, you can take a much simpler network like ResNet 18, a much smaller network that might be more readily applied to a IoT use case or whatever it may be, and actually get significantly better results than just fine-tuning the experiment transfer version of a much larger network. So gains are to be had in both, but again, going back and fine-tuning can actually produce significantly better results, which was an interesting result for us because experiment or transfer learning is obviously a very popular topic in the field today, but many of these problems, when even slightly modified, you can get significantly different results by doing that full tuning. So again, what this does is it takes a potentially intractable task of tuning a large network on a large computer vision data set and makes it both tractable in terms of wall clock time as well as total compute budget utilized by doing this intelligent multitask optimization. And you can get significantly better results by tuning that larger network, and getting significantly better results even beyond the transfer learning approaches that are very popular today. So I'll pause there and see if there are any questions. Again, I went over 4 different techniques here, both the kind of classic Bayesian optimization problem that you're probably facing today. I talked about extensions to it, like multi-metric optimization, where you can rephrase it into tuning multiple competing metrics. We talked about how to leverage the full compute infrastructure that you may have already invested in to get to the same or better results and faster wall clock time. And then finally, we talked about kind of tuning the untunable, things that would be completely intractable in a more naive optimization setting, but can become tractable when you leverage things like more intelligent adaptive design of experiments, especially when combined with things like multitask learning. So these are again, a set of examples that we've seen in the real world, examples of fresh, very groundbreaking research that we're constantly adding to our ensemble. But it only is scratching the surface to the types of kind of real world applied, messier optimization problems that we pride ourselves in being able to attack. Again, the goal of SigOpt is to take your optimization problem and instead of giving you an optimizer problem of having to deal with brittle open source, effectively solving that problem and all of the different edge cases and ways to phrase that problem. And if you have any questions, we would love to answer them now or follow up independently and talk about how we can actually get you access to this yourself. So with that, I'll hand it back to Nick, who I think has been moderating some of the Q&A.
Yep, thanks, Scott. Appreciate that. And thanks for the presentation. The first question relates to, it's very easy question to answer. It relates to whether these slides will be distributed afterward. We will distribute the slides as well as a recording of the presentation, and we'll be sure to send that to everyone who attended today. Second question relates to some of the broader context that you shared up front. I guess without going further into it, the question asks more or less like what outside of the kind of advanced features that you spoke to here did you cover during your talk at TWIMLcon at a really high level? Trying to get a sense of how to think about us in the broader modeling stack.
Yeah, so I talked about different trade-offs, just jumping back here. Different trade-offs in this larger kind of modeling stack that you may be investing in today. Things around what's worth building bespoke solutions for. And we've seen a lot of our customers realize that they have very unique data associated with the different things they're attacking. Large companies building recommendation engines that use us are very different than companies building algorithmic trading strategies, which are very different than our customers in the oil and gas industry. So there's a lot of custom tooling that usually goes into data preparation, as well as the actual productionalization of those models. High frequency trading strategies look fundamentally different than fraud detection strategies or recommendation engines, etc. So a lot of custom work is often done at the ends here, both in how you ingest data and how you actually deploy your models. But a lot of times, flexibility is what's required in the middle. This is about how do you take that unique data and that unique application, but really make sure that you're building the best possible thing in order to attack that problem. And so from the customers that we work with across the world, we see that they usually like to maintain as much flexibility as possible within the terms of their modeling frameworks, using the right tool for the job. That might be scikit-learn and random forests or GBMs for certain tasks. That might mean deep learning or reinforcement learning for other tasks. But then they also might have different hardware requirements. So bespoke solutions on the edges, flexibility on the top and the bottom here. But the nice thing about having an experimentation and optimization platform is allowing you to have that flexibility and standardize on something that all of these models run into, like experimentation optimization, without constraining the modelers in any way. So the talk goes into quite a bit more detail about trade-offs between different aspects of this, different things that you need to think about in terms of building versus buying, et cetera. And we'll make that available as part of the end of this webinar as well.
Great. Those are the only 2 questions that we got today. So without further ado, I'll say thanks, Scott, today for presenting this content, and thank you all for attending. Be on the lookout for the slides from this webinar, as well as a video recording that you can share with your colleagues. And thanks again. Join us for, last thing I'll say is join us for upcoming webinars that we'll be hosting on related content going into similarly technical content, as well as some higher level content that we'll be marketing through social media and emails. And look for us at NeurIPS. It's never too early to start talking about NeurIPS. We'll be there in December if you're attending as well. We'd love to schedule a pull-aside meeting with you. We'll have a good swath of our team there as well. So look for us there too. So thanks again for engaging with us, and we'll see you next time.